In this video, we have a tutorial of causal linear time invariant system defined by a second order difference equation. That is, we have y of n plus 2 minus 0.6 y of n plus 1 minus 0.16 y of n, and this is equivalent to 5x n plus 2. So this is our second order difference equation. And moreover, we have some initial conditions which are y of minus 1 is 0 and y of minus 2, that is at minus 2 time unit, the output is 25 by 4. And meanwhile, we also have an input that is x of n, and this is equivalent to 4 power minus n u of n. And we are asked to find the total response y of n. So this particular example I have taken from Linear Systems and Signals by B.P. Lathi. So presently this expression is an implicit expression, but the total response would be in terms of an explicit expression that would not account for any present or past values of output. So the output would have some function that we need. So we know that the solution of this problem, that is the total response y of n, so this is actually equivalent to a zero input response when the input is 0, and then we have a 0 state response when we set the values of states equal to 0. So addition of these two responses would yield the total response. So let us first move towards finding the 0 input response. Herein we would perform a simplification of this expression. So say this is our expression number 1. So from 1, so we can define the delay by a variable, say e. So the first expression would simply be an e square, because over here we have a time advance of 2 units, so we have induced e to the power 2 minus, from here this coefficient would be 0.6, and actually the advance is of 1 unit, so we have 0.6 e, and we have the present time with the constant coefficient 0.16, so we have 0.16, and all of these are yielding the operationally simple form, which is now in terms of e's rather than delays. Similarly, on the input side, there's a 2 unit advance, so we have e square, and then we have x of n. So say this is our second expression. But since over here we are interested in the 0 input response, so that would mean that this input is 0, and we can say this is 0, and this would lead to y naught of n, that is the output response when the input is 0. Similarly, the roots of this polynomial expression would be e1 plus 0.2 and e2 minus 0.8. Now this equation has two roots, so the solution of this expression, that is the characteristic equation, which we often refer to as yc of n, over here this is simply y naught of n. So this would be of the form, because of second order difference equation, so we would have a coefficient c1 multiplied by the first characteristic root to the power n plus coefficient c2 with the characteristic root e2 to the power n, and plugging in the values of these roots, so we have e1 is minus 0.2, and similarly e2 is plus 0.8 per n. So say this is our expression number 3. Now in order to find y naught of n, we need to find the values of c1 and c2, and for such we will use initial conditions. That is, y of minus 1 is 0 and y of minus 2 is 25 by 4. So we can say that when n is minus 1, so y of minus 1 is 0 from here, and this is equal to, from this expression, c1 minus 0.2 to the power minus 1, because we have set n equal to minus 1, and then we have c2 which is 0.8 power minus 1. Say this is our expression number 4. And similarly for n equal to minus 2, we have y of minus 2, and the value for that is 25 by 4. So this is simply 25 by 4. Again we have c1 which is minus 0.2 to the power minus 2 plus c2 0.8 to the power minus 2, and this is our expression 5. So from 4 and 5, so it is easy to calculate c1 and c2. So c1 is simply 1 by 5 and c2 is 4 by 5. Now plugging c1 and c2 in our third expression, so the zero input response, that is the response which is only based on states, is simply 1 by 5, and then this part which is minus 0.2 power n plus 4 by 5 0.8 power n. So this is our first solution, and that is the zero input response. So we have basically found out the first part. Now let us move towards the second part, that is the zero state response. So we know that the zero state response ys of n is equal to the impulse response h of n convolved with the input x of n. So in the question we are given with the information of the input, that is x of n, which is 4 power minus n u of n. However, we do not have h of n. So h of n we need to find. And for such, there is a formulation again in the book of linear systems and signals by Lati, where we define the input output difference equation in terms of a generic form, that is a sum form, and we say that k is 0 to capital N a n y of n minus k, and this is equivalent to k 0 to again capital N b n x of n minus k. Now again this is a difference equation, that is particularly this is LCCDE, linear constant coefficient difference equation of nth order. So previously in this example we have the second order difference equation, which is over here. So according to that, this is our a naught into y of n plus 2, this is our a1 into y of n plus 1, and this is our a2 into this. Similarly, we have a b0 b1 which is plus b2 which is again a 0. So if we have a difference equation of the second order or of the nth order, so we can find the impulse response h of n. by this expression, that is bn by an delta of n plus the characteristic equation yc of n into u of n. So this u of n defines that h of n is a causal system. So this system is actually causal. So the impulse response would be 0 and onwards. And yc of n is already defined over here in equation number 3. So that is already available to us. But right now we need to simplify this by finding the values of bn and an. Now over here this an is this nth value, that is the lost coefficient, and similarly bn is this lost coefficient. So let us look into an. What is an? So our an is basically a2, and that has a value of minus 0.16. So an is minus 0.16. Note that for this we have set, as per this k, we have set equal to 2. So when we set k equal to 2 in bn over here, and b2 is 0 into x of n, so b2 is 0 here. The lost coefficient is basically 0 as per this difference equation. The lost coefficient n, right? So this means that bn is 0. So in this case we can simplify this and we can say our h of n is simply bn by an, but bn is 0, so this whole part would cancel off. So we would have the characteristic equation yc of n times u of n, and we have already known the characteristic equation from equation number 3, which is over here. So this is simply c1 0.2 power n, that is a minus 0.2 power n, plus c2 0.8 power n. And for this we are saying that n is greater than or equal to 0. So this is actually our impulse response, h of n. Now again we have these two coefficients c1 and c2 that we need to find so that we can have the closed form expression of h of n. But note that we cannot use the states here because we are considering that the second solution is a zero state response, right? So we cannot assume the states. So what we can do is, let us rewrite the difference equation which was over here again. Now we delay both units, that is left hand side and right hand side, by 2 units, since the system is LTI and more precisely it is time invariant. So hence we would have y of n, and this is equal to 0.6 y of n minus 1 plus 0.16 y of n minus 2 plus 5, and input would also be delayed, right? So this is x of n. So this is now our remodeled difference equation. So we know that in a given system we have an input which is x of n and the output is simply y of n. So if the input is delta function, that is delta of n, then the output would be impulse response, which is h of n. So hence in this expression we are going to change x of n, that is the input, to a delta function delta of n. So this would yield the output y of n, and that would be simply h of n. So hence our h of n, when we have this input as delta of n plus the other terms which are simply 0.6, y of n minus 1 would convert to h of n minus 1 plus 0.16 h of n minus 2. Now this is our impulse response in terms of past values of impulse plus delta function. So note that what we need to do is basically we need to find this expression, right? And we need to specifically find the values of C1 and C2. And for that we wrote the difference equation, use a delay, and then afterwards change the input to delta function, so the output changed to impulse response. Now if we use an iterative approach, we set n equal to 0, so we would have h of 0, and we would have 0.6 h of minus 1 plus 0.16 h of minus 2 plus 5 delta of 0. But h of minus 1 is 0 since the system is causal, and h of minus 2 is also 0. So this is because the system is causal. And for causal systems, impulse response would always start from 0 and go onward, right? It can never be from leftward, that is minus 1 or minus 2, and so on, right? And similarly the delta function is simply 1, and 1 multiplied by 5 would yield a simple 5. So h naught, that is h of 0, is simply 5. Similarly, when n is equal to 1, so we have the time unit 1 and 0.6 h of 0 plus 0.16 h of minus 1 plus 5 delta of 1. Now again, because of causality, h of minus 1 would be 0. Though h of 0 is now 5, so now 5 would be multiplied by 0.6. So this would yield simply a 3, and delta of 1 is 0 because delta is only available at time 0, right? At time 1 the value is 0, so this is basically again a 0. So overall we have 3. So there were two coefficients, that is C1 and C2, in this expression, and now we have two conditions, that is h of 0 is simply 5 and h of 1 is 3. Now inserting these auxiliary conditions on h of n, so we would have, when n is 0, h of 0 is 5, and this is simply C1 and minus 0.2 power 0 plus C2 0.8 power 0. Whereas when n is equal to 1, h of 1 is 3, and again we have, and this is minus 0.2 power 1 plus C2 0.8 power 1. So from these two we can find C1 and C2, and precisely they would be simply 1 and 4, right? And we can plug these 1 and 4 in the aforementioned h of n, which is this one. So we have simply minus 0.2 power n plus 4 into 0.8 power n, and this is for n greater than or equal to 0. So this is our impulse response. Now we have found out the impulse response of this function or the system, and if we have found out the impulse response, so the zero state response suggests that if you have the impulse response, all you need is just the input and you can convolve that with, so you would get the zero state response. So basically y s of n is this convolved with the input s of n, right? And this is simply minus 0.2 power n u n from here. This is going to convolve with the input, which is simply 4 power minus n u of n plus, again we have 4 over here, so 4 0. Power n u of n, and this is going to be convolved with the input again, that is 4 power minus n. Now simply for this, the solution would be in terms of a summation, and say we're going to flip this part for convolution, and we're going to keep this as it is. So this is simply 4 raised to power minus k, and we get the summation variable as k. So the summation, because both of them are unit step functions, they're going to start from 0 and it is going until n. So over here we would have a minus 0.2 from point n minus k, and similarly you would have the same procedure over here. So a couple of steps more. So you would have this k is this n is not a part of this summation, so we can have it outside. That is, we can have a minus 0.2 power n outside the summation, and then we would have similarly you can solve the other part as well. Now we can apply the formulation, that is 0 to n alpha power n. So we simply have 1 minus alpha n plus 1 over 1 minus alpha. This is a geometric series formulation. So eventually you would get a solution over here. So let me call the solution as B. So this is our zero state response, right? So once we get this zero state response in closed form, we already have the zero input response, which is over here. So adding these up over here, we will get our total response, which is y of n. So note that these sort of problems can also be solved by means of z transform and the transfer functions in the discrete time. So if you have any comments or suggestions, please leave a comment in the comment section below. Thank you.